Everything you want as a creator comes from making the best videos possible, and thumbnails.
Most how to grow on YouTube videos tell you to use catchy thumbnails and clickbait titles.
It didn't just go viral randomly. It either was a good title, thumbnail, the content, something.
Over 3 genius title and thumbnail strategies that could explode your views and...
But what if I told you there's an actual scientific approach behind YouTube's recommendations? In this video, we're diving into a groundbreaking deep learning paper from Google that explains how YouTube decides which videos to recommend, and trust me, it's way deeper than just get more watch time. Hey everyone, hope you're doing great. We're back with another video, and today we're diving into something really fascinating, YouTube's recommendation system. This is one of the most advanced and large-scale recommendation engines in existence. It works based on an important research paper published by Google in 2016.
What? Sir, yes, sir!
Now, while this paper is from 2016, and the architecture has likely evolved since then, perhaps incorporating transformer models or other recent advancements, the fundamental principles still hold. The basic problem remains the same. How do you recommend the right videos to users in a way that maximizes engagement and satisfaction?
Well, let's dive in.
The paper outlines several challenges that make YouTube's recommendation system particularly complex. Scale. YouTube has billions of users and an enormous number of videos, with countless hours of new content uploaded every minute. This makes retrieving and ranking videos a highly complex task.
Viewers globally streamed over 1 billion hours of YouTube content daily on their TVs in 2024.
New videos are uploaded constantly, and recent content is often more relevant to users than older videos. The system needs to detect and prioritize fresh content quickly. User behavior on YouTube is noisy and unstructured. People watch videos for many different reasons, and their actions don't always indicate clear preferences. What exactly should the system optimize for? Watch time, user satisfaction, retention. The right objective function is key to making good recommendations.
Oh well.
I see. So they use a two-stage recommendation system. Okay. Candidate generation. This is the first stage where the system quickly selects a few hundred videos from the massive YouTube catalog based on broad user preferences. In the second stage, a more computationally expensive model refines this list by analyzing many more details, ensuring the final recommendations are highly personalized. During development, they make extensive use of offline metrics.
Oh yeah.
To guide iterative improvements to the system. However, for the final determination of the effectiveness of an algorithm or model, they rely on A/B testing via live experiments. In a live experiment, they can measure subtle changes in click-through rate, watch time, and many other metrics that measure user engagement.
So if we dive deeper into this,
So previously, matrix factorization approach trained under rank loss was used. The candidate generation system is built as a deep learning model that frames video recommendations as a classification task. Essentially, it predicts which video a user is most likely to watch next at a given moment, given their watch history and other contextual factors.
the model treats this as an extreme multi-class problem. The goal is to predict that user watches video at a given time t given user and context.
Some definitions. Each video VJ and the user context pair U are vectors in the same high-dimensional space. The dot product VJ.U measures the compatibility between a video and the user context. These compatibility scores are passed through a softmax function to produce a probability distribution over all possible videos. The video with the highest probability is the one most likely to be watched by the user at time t. To handle millions of output classes efficiently, the model uses candidate sampling, sampling a few negative classes instead of computing softmax over all classes, and corrects for bias using importance weighting. This greatly speeds up training while maintaining good performance. Although hierarchical softmax is another option, it performed worse due to its structure forcing difficult and often unrelated classification decisions. Serving time, we need to quickly find the top and most relevant videos to show a user. To solve this, they use an approximate scoring method that is based on hashing.
In the first pass, it is just an approximation.
Every video is represented as a dense vector or embedding. These embeddings are learned automatically by the model during training, not predefined. Importantly, they are trained along with the rest of the neural network using standard gradient descent and backpropagation. That means the model updates both the video vectors and the rest of the neural network weights at the same time. Okay, this is the architecture of their candidate model.
So important thing here is that there is a search history along with the purchase history. This is very important. So this means like your YouTube channel, I think it depends on the search history.
Search history is treated similarly to watch history. Each query is tokenized into unigrams and bigrams, and each token is embedded.
It's like then it is averaged out and a dense vector is generated. There are users with no watch history, so having demographic information does help. Region and devices are also unbattered, along with binary and continuous features like gender or age logged in state. And these values are generally normalized to the 0 to 1 range.
So if think of freshness, machine learning systems often exhibit an implicit bias towards the past because they are trained to predict from historical data. To address this, the example age feature is added. During training, the age of each example, how old the video is included as a feature. At serving time, this feature is set to 0 or slightly negative, telling the model we're predicting for right now.
These experiments, a vocabulary of 1 million videos and 1 million search tokens were embedded with 256 floats, each in a mixed bag size of 50 decent watches, then 50 decent searches. The softmax layer outputs a multi-nonlinear distribution, or the same 1 million videos, classes with the dimension of 256. These models were trained and converges all YouTube users corresponding to several epochs over the data. Network structures followed a common tower pattern in which the bottom of the network is verticest. Each successive hidden layer halves the number of units. Still about the second phase of the model, which is ranking. About ranking, they use impression data as a way to rank. So for example, a user might watch a given video with high probability, but it is unlikely to click on a specific homepage impression due to the choice of command image. During ranking, we have to access too many or more features describing the video and the user relationship to the video, because only a few hundred videos are being scored, rather than being scored in candidate generation. So this is exactly where they talk about like thumbnails, but the thumbnail, they're saying that thumbnail is not the only factor. So if the thumbnail is not good, but we still won't be recommended because the video is high quality. So that's what they're saying here actually. And then they're saying here is that they need to accept many more features describing the video and the user's relationship to the video, because only a few hundred videos are targeted here. So they use Eve neural network with similar architecture as above to assign an independent score. The list of videos is then sorted by the score and returned to the user. Final ranking objective is constantly being tuned on the live testing ground. I think there's mentioned somewhere they use logistic regression. Yeah, video impression using the logistic regression.
The categorical features they use vary widely in their cardinality. Some are binary, example whether the user is logged in, while others have millions of possible values, example the user's last search query. Features are further split according to whether they contribute only a single value, univalent, monosuperiority, or a set of values, or multivalent. An example of a univalent categorical feature is the video ID of the impression being scored, while a corresponding multivalent feature might be a bag of the last n video IDs the user has watched. They also classify features according to whether they describe properties of the item, the impression, or properties of the user context, per query. Oh yeah, query features are computed once per request, while impression features are computed for each item scored. For example, consider features that capture a user's past interactions with the channel that uploaded the video being scored, such as how many videos the user has previously watched from that channel, or when they last watched a video on a similar topic. These continuous features summarizing past user behavior are especially powerful, as they generalize well across different videos and topics. Additionally, it's crucial to carry over information from the candidate generation stage into the ranking stage. One important type of such feature is which source or model nominated the video as a candidate, as this context can influence the final ranking decision. Features that track how often a video has been shown to a user in the past, but not watched, are important for introducing churn in the recommendations, ensuring that the user doesn't see the exact same list every time. For example, if a video was recently recommended but the user ignored it, the model will learn to lower its ranking the next time, making the recommendations feel more dynamic and relevant. Just like in the candidate generation stage, they use embeddings to convert sparse categorical features into dense vectors that work well with neural networks. The goal of the model is to predict expected watch time based on whether a user clicked, positive example, or did not click, negative example, on a video. For each positive example, they also include the actual amount of time the user spent watching the video. To achieve this, they apply weighted logistic regression, a technique specifically designed for this task. The model is trained using cross-entropy loss. At inference time, they apply the exponential function e to the x to the model's output to produce a score that closely approximates the expected watch time for a given impression.